Here's a name that trips up nearly everyone the first time they meet it. Logistic regression is not actually a regression model at all. It is a classifier. It answers yes or no questions. Is this email spam? Will this loan default? Is this tumor malignant? It starts from the very same weighted sum that linear regression uses, and then it does one clever thing to bend that raw number into a genuine probability. That single twist is the whole trick, and it's what makes logistic regression the most widely used classifier on the planet. Let's dig in. So what's wrong with just reading a plain linear score straight off? Here's the problem, side by side. Feed features into a plain linear model, and you get a raw score that could be anything -40, 0, 107. What does that even mean as a chance of spam? Nothing obvious. There is no natural cutoff, no calibrated meaning, and comparing two of those scores tells you almost nothing useful. You cannot hand a raw logit to a doctor or a lender and expect a sensible decision to come out the other side. Logistic regression squeezes that same score into a clean probability between 0 and 1. Now the output is honest. A value of 0.9 really does mean the model is highly confident, and you can set a sensible threshold, rank cases by risk, and make decisions you can actually defend. So how does a single prediction actually get made? Walk the path from raw features all the way to a final label. Start by taking the weighted sum of the features, exactly like linear regression. Each input times its own weight, all added together with an intercept. That gives you one raw score, sometimes called the logit, which can land anywhere on the number line. Now, push that number through the sigmoid, the elegant S-shaped logistic curve. It takes any value, however large or negative, and gently squashes it into the range 0 to 1. A big positive score maps near 1, a big negative score near 0, and the result reads as a probability. Then compare that probability against a threshold, usually 1/2. Above the line, the model leans positive. Below it, negative. And here's the useful part. You can move that threshold to trade caution for coverage, depending on whether a false alarm or a miss costs you more. Finally, output the class. Spam or not spam, default or safe. Under the hood, the weights were learned by minimizing log loss, the objective built specifically for probabilities, which has no closed form, and so is fit with gradient descent. Strip it down, and 3 ideas define logistic regression. It is a linear score squashed by the sigmoid. The same weighted sum as linear regression, but bent through the logistic curve, so the output is a probability instead of an unbounded number. It is trained by minimizing log loss, also called cross-entropy. That's the right objective for probabilities. It rewards being confident and correct, and punishes being confident and wrong. And there's no closed form, so we use gradient descent. Its weights read as interpretable odds ratios. Exponentiate a weight, and you learn exactly how the odds of the positive class change per unit of that feature, which is gold in regulated fields where you must explain a decision. And with softmax, it stretches gracefully from 2 classes to many, becoming multinomial logistic regression. All right, let's lock in what matters. Despite the name, logistic regression is a classifier that pushes a linear score through the sigmoid to output a probability between 0 and 1. It compares that probability to a threshold to pick a class, and it is trained by minimizing log loss with gradient descent, not squared error. It is the workhorse binary classifier behind spam filters, credit scoring, and medical risk because it is fast, calibrated, and its weights read as odds ratios. Its limits mirror linear regression. It assumes a linear relationship in the log odds, so curve boundaries need feature engineering. Hungry for more machine learning unpacked without the fog? That's our whole mission at Standarity.com. We'll see you there.